Okay, so this is task 1 still. This time the questions we're going through, not the explaining everything part of it. This is the second video of 2. So I'm going to go through the questions. I'm going to make use of the mark scheme quite a bit. I will use the webcam in the corner to go through a few questions, a bit more detail if I need to write anything out. But I'll make use of the mark scheme, skipping backwards and forwards to show you the key parts. So first question is really straightforward. It's just stating the part of the electromagnetic spectrum where it actually belongs to. So we've spoken in the past that you need to know which frequencies are related to which part of the spectrum, which wavelengths therefore related to which part of the spectrum. This is mainly the visible part of the spectrum. When we say it's -7 meters, very large is radio, and very small wavelengths are generally gamma and X-ray. So let's scroll down and double check that. Actually no, let's do the next part of the question first, the next question, and then we'll scroll down and check afterwards. So they're asking you to show that cesium has a work function of about 3 × 10⁻⁹, so joules. Okay, so that's what we want. So we must have somewhere the idea of a threshold frequency or a wavelength that actually is releasing electrons. So the maximum wavelength of electromagnetic radiation that can reach photoelectrons is 6.5 × 10⁻⁷. So let's make this word come slightly bigger. Okay, we know that the work function is equal to h times f0, which is threshold frequency times Planck's constant. So what we can do is we can change this slightly because we want wavelength instead. Well, we know speed is equal to frequency times wavelength. Okay, we know that when it's light, the speed of light is equal to frequency times wavelength, so therefore the speed of light must also be equal to the threshold frequency times the threshold wavelength. So we can rearrange this idea, this equation here, for threshold frequency, and therefore substitute it in here. So threshold frequency is equal to speed over threshold wavelength. Let's put that in. So that would C over lambda naught. Okay, so 6.63 times 10⁻34 Planck's constant times 3.3 times 10⁸ speed of light. And then we've got our threshold frequency, so threshold wavelength here of 6.5 times 10⁻⁷. Okay, so let's whack that through our calculator. Okay, and see what we get. Sorry about the messy writing. Again, that's something you guys should know about me by now. So let's type that through. So I'm going to do it step by step because I've got my older calculator here. I know I'm moaning at you guys about calculators. I keep my older one at home. Right, so 34 times 3 times 10⁸. So that's my top line. I'm going to divide that by 6.5. So is it? EXP, I think it's 7, not 17. I've written 17 here. It's supposed to be 7. -7, sorry. Okay, so I end up with 3.06 times 10⁻⁹, which we can see is pretty close to our answer. Nice question to get. Let's see how many marks it is. It's a 2-mark question. Okay, so it takes about 2 minutes to do. 2-mark question. So that's quite a nice question to get. A lot of people get tricked up by the fact it's a threshold wavelength and not a threshold frequency, which is what we're used to. Next question. So once we get through this, or as part of this question, we're going to check the mark scheme and check we've got the first 2 right as well. So explain what is meant by the term stopping potential. So I've done a typical teacher thing of going right to the question, not reading what's happening above it. So we've got the cesium cathode on the photocell. It's got radiation actually coming down onto it. The circuit is shown measuring the potential difference for a range of frequencies. Okay, so we've got a stopping potential taking place. Remember, stopping potential is the voltage or the potential that stops photoelectrons having kinetic energy. So if they have no kinetic energy, the stopping potential must be the voltage that's actually being applied in this situation. Right, okay. So now we've got a graph. This is the last part of this question, so we're going to check the mark scheme after this. We've got 3 graphs here. Sorry, 1 graph with 3 lines on it for 3 different metals. So we know from our previous video that these lines are parallel due to the fact that the gradient is Planck's constant. So we'll see if the question's asking about that. And remember, these have different work functions. So in this situation, that's got the lowest threshold frequency, cesium, so therefore it's got the lowest work function, while beryllium will have the highest threshold frequency, therefore the highest work function. So the experiment is now repeated using different photocells, therefore different metals, to measure the stopping potential of calcium and beryllium. The graphs show stopping potentials that are, so that's Vs of all three metals vary with frequencies, so how they're varying with different frequencies. So use this relationship to explain why all three graphs are parallel. Well, the graph we've got is Vs against F. So we want to rearrange the equation, so we've got Vs on as the y part of the equation, and F as the x part of the equation. So remember, we use the idea of y equals mx plus c for proving things with graphs. So our expression that we're trying to rearrange is hf is equal to EVS plus phi, which is a work function. So we've got the electron voltage, so it's in other words, this is an energy here, so that's the kinetic energy. It's just stopping potential times the electron volt is equal to the kinetic energy. That's the kinetic energy term as part of this. We know that these two are added together. So hold on, that's my previous video I've just finished doing. Let's get that out of the way. So that's the energy of the photon coming in, that's the kinetic energy, and that's the work function. They've just put the kinetic energy into electron volts essentially. So remember that voltage gives us a stopping potential, that's why we can do that. So this part here is our EK term. So we want this Vs part of it on our Y, and we want everything else on our X. So we want this bit by itself, so we can have it as part of our Y-axis, and we want F as our X. So let's rearrange for this. So if I bring this over onto this side and have this by itself, so we end up with EVS is equal to HF minus the work function. Okay, I now want to get rid of my E. It's not particularly useful on this side because if we look at our graph over here or in the Word document, they want it as VS, so we need to get it to VS by itself. So VS is therefore going to be equal to HF minus the work function over E. Okay, now it's just slightly different to the way I've been through one of these in class. In class we didn't have to rearrange for to have Vs by itself. We rearranged to have a different part by itself over here. It was the whole kinetic energy, not just a stopping potential. So if we now look at this graph, this is our y, or sorry, look at this equation, that's our y, that's on the y-axis of our graph. The x-axis of our graph is f by itself. Okay, so remember, in front of x you're going to have m, so whatever you're multiplying your x by, that must be m, so that's h over e is your m. And over here we have the work function, so that's going to be our plus c. So let's write that out neatly. Our y is Vs, let's write it underneath. Our m is this h over e rather than being h, which is what we're used to. X is f, and our c, as per usual, is the work function. No, it's a work function over the charge of an electron. Because technically, let me explain why. Just being a bit silly there, sorry. This can be split into two separate things, like that. So if I did y equals mx plus c individually on those, sorry, split into two separate things like that. So if I did y equals mx plus c on those two separate bits, then there'd be two separate entities. So that would be, there's your plus c as those two parts there, and there's your m. So you've got to be very careful when using y equals mx plus c. So there we go. So the gradient is always going to be parallel because both of those are constants. Okay, the work function and charge of electron are constant. So let's check in the mark scheme that our answers for the first section are correct. So that's question 1. All the way down in the mark scheme. Here we go. So question 1, let's have a look. Yes, a light, visible, either of those have been fine. If you got more specific and said red, it's fine. So it's even better, but light is fine by itself. We got a value about, we got that exact value actually, that's exactly what we got. So it's the minimum potential difference between C and A is a better way of putting it, or which reduces the current to 0 or stops electron reaching A, which is the idea we were saying. So it doesn't allow the release of electrons or electrons to cross between C and A in terms of that diagram. Okay, so yep, there's the rearrangement I did. So yes, look carefully. I did miss that out the first time, but I stopped and corrected myself, as all good physicists do. So the gradient is HE, which is constant. That's the idea. Okay, so that's everything that we've been through there for the first question. Okay, so look at question number 2. So magnesium is a work function of value there, so it's nearly 6 times 10 to the minus 19. Explain what is meant by the statement. Well, we know the meaning of work function. Work function is the minimum amount of energy required to release a photon electron from the surface of metal. Look back in your textbook, look back in your notes, look back in your explaining everything. That's a standard definition. So ultraviolet from an extremely faint source is incident only on a magnesium plate. The radiation is, or you can see it's very, very low intensity. Single magnesium atom occupies an area of about 8 times 10 to the minus 20 meters squared on the surface of plate. Show that the radiation if the radiation is regarding wave motion, it should take 200 seconds for it to absorb that much energy. Well, okay, if we want to get to energy and we've got time, you first thing you should always think about is power. So the first equation that we're really going to be using in this situation is, one of the equations we'll really be using in this situation is power as energy over time. We know we're going to have to show energy, so let's make energy the subject of the equation. So energy is equal to power times time. Okay, we've got an idea here to do with intensity as well. So remember, intensity, we've got the idea of power is equal to flux over area. So that's also going to be tied into this. We've got the flux, we've got the, I made another mistake there. It's flux times by area. It's a Sunday afternoon, I'm allowed to make mistakes. It's flux times by area. At least I'm spotting myself doing them. As a common mistake, actually, it's good to actually make that mistake, he says, is pointing out the idea that most people remember that pressure is force over area, so you're used to write P is F over A, so remember that power is flux times area if you're doing that one, so F is equal to P over A. So we want to figure out the power, so we don't need to make F the subject of the equation. So we've got the flux, I'll highlight that in there, the intensity in other words. Okay, we've got the area, that's that there, so you multiply those two together, and then you need to, that's your power essentially, and then you want to figure out your energy, so you need to times it by 200 seconds to figure out your energy. So let's have a go at that, let's see whether we can do it. So we've first got our intensity of 0.035, and we're going to multiply that by, sorry, let's make the webcam a bit bigger, you guys might be able to see it a bit clearer then. Yep. So we're going to multiply that by 8 times 10 to the minus 20. Very small atom. It's an atom, of course, it will be very small. Then we're going to multiply that by 200 because it's 200 seconds it's happening over. Okay, so you get about 5.6 times 10 to the minus 19, which is pretty much what they're after. So it's absorbing about that much. So I'm a bit concerned that that's about 0.29 out, so I'm just going to double check to see if I made any silly mistakes in the mark scheme. You can see that today's a day of silly mistakes for myself. Just want to make sure I haven't made another one. Right. No, it seems like I followed it through correctly. They've just used I instead of F as their letter. Yep, that's exactly what I multiplied through. For some reason I've got 210 seconds here. Okay, there's our different. Okay, so I'm guessing they want us to show the time, show how the time is close to 200 seconds, so I did make a mistake. Let's double check reading the question. That's right. Oh yes, so it should take at least 200 seconds. So technically what you need to do is rearrange this equation here for time instead. So what you do is actually do work done, sorry, you do energy over power to figure out how long it will take. So let's go through that so I can show you what we need to do there. So we figure out the power exactly the same way as before. So if we scroll up so we can see our numbers. There we go, so it's 0.035 times by 8, sorry, times 10 to the minus 20. Okay, so that's our power. We want to do 5.89 exp minus 19 divided by that answer. So that ends up being 210, which is exactly the answer they got. 210 seconds about. Excellent. Right, let's continue working through this. In practice, it is found that the photo emission from plate begins as soon as the radiation source is switched on. Explain how the photon model of electromagnetic radiation accounts for this. You will be awarded a mark for clarity of your answer. Right, okay, so quality of communication question, 4 marks. Okay, right, so we know we've got to talk about photons interacting with one electron. Okay, we know we've got to talk about the fact that photons are packets of energy, and the fact that it's frequency dependent. So the energy that each of these photons has is frequency dependent. There are main terms that we've got to tie into this. So let's see what the mark scheme says. So the idea of frequency dependent. Okay, so you can see that straight away over here, frequency dependent or wavelength dependent. You could have put one photon, one electron, so it's ejected immediately as well as a key term. And you can't just say it's just photoelectric emission is immediate. Okay, and the final marks from the quality of its communication. Okay, next question. So again, a nice question to get, although I made a silly mistake. I'm sure you guys won't. Right, question 3. So a leaf is, you've got a leaf, it's tilted towards the sun, it's receiving solar radiation of 1.1 watts per meter squared. So I automatically turn that into watts per meter squared. We know we want it in watts per meter squared. You've also got this angle of 50 degrees in there as well, which is going to probably become important at some point. The leaf is almost circular. It's got an average radius of 29 millimeters. Right, straight away into meters. It's 29 times 10 to the minus 3. It's almost circular. Automatically pi r squared. You've got to think about. Show that the power of the radiation perpendicular to the leaf is approximately 2 watts. So again, right, we've got to tie in. So it's a 3-mark question. Okay, so we've got to tie in the idea of pi r squared to figure out our area. Okay, we want to convert the intensity into watts per meter squared, so that's 1100 watts per meter squared, and we want to convert the radius into meters, so that's 29 meters. Okay, so figure out what the area is, then we're going back to an equation we've used before, which is power equals flux times by area, and we need to figure out our power. Now, a good way to check to see whether the 50 is important is put it through and see whether the value is anywhere near the 2 watts you actually need. And if it's not, the idea that 50 has to become important. We clearly know it has to be, okay, as we actually do it, but let's just check we're approaching this with our correct thinking. Okay, so the idea is that the angle was 50, so using cos 40 or sine 50 would actually tell you the angle alongside intensity, because remember sitting at an angle, would tell you the actual intensity that actually hits it. Okay, so power is equal to intensity times area, or flux times area. Okay, that's pretty straightforward. Then you tie in the fact that intensity or area is going to have this idea of sine 50 or cos 40 attached to it because of the fact it's at an angle, and then it literally is multiplied through straight away, as easy as that. So you can see the calculation below. A very nice question to get. Next, again, a few people will be tripped up by the idea of the fact it's at an angle, although it is just literally a multiple through of cos 40 or sine 50 by thinking about that as a triangle and using trigonometry. Right, so next part of it. Calculate the approximate value of the energy received for the leaf during 2.5 hours of sunlight. So 2.5 hours, okay, so you need to convert that straight into minutes. So 2 hours is 120, so 2.5 hours will be 150 minutes. Okay, you need to turn those minutes then into seconds, so 150 times by 60. So 150 times by 60. Okay, so that's 9,000 seconds. And then you've got to turn, remember from before, we've put it on here, energy is equal to power times time. So we need to times that, multiply that by the power, and we need the power something like 2.2 or about 2. Remember, if you haven't got that the question above correctly and use 2, they won't penalise you for that. So it's about 19,000 H, it's about about 20,000 joules. So let's double check. Question number 3, 20,000 joules. Brilliant, 20,000 joules, nice and straightforward. Okay, so question 4. Question 4 is asked about photoelectric effect. So plenty of these questions in there. We know it comes up often. So photoelectric effect supports particle theory of light, but not the wave theory. Below are 2 features of photoelectric effect for each of you to explain why it supports particle theory and not the wave theory. Emissions of photoelectrons from the surface of metal take place instantaneously. Okay, the explanation is because each photon has the same amount of energy, and each photon interacts with one electron, therefore releasing it. If it was a wave, it wouldn't do that. The energy would build up over time. The incident light with a frequency below a certain threshold frequency cannot release electrons from the surface of metal. So remember that saying essentially that the energy of a photon is frequency dependent and not dependent upon intensity. Intensity is only, remember, varying the number of photons. Okay, so the energy of the photon depends upon the frequency, and therefore a specific frequency is required for there to be a release of a photoelectron from the surface of a metal. Okay, and remember that frequency therefore ties in with work function as an amount of energy by multiplying by Planck's constant. So we can see what to say about that one, question 4. So particle theory, one photon attracts one electron. Okay, wave theory would allow energy to build up. Brilliant. Okay, so particle theory, a frequency too low would have not enough energy. And remember, in wave theory, again, it would not any frequency beam would actually release an electron. It would just build up over time. Same sort of idea. Excellent. All right, question number 5. This is the last question. So I've been talking for about 12 minutes in the first video, and I'm sure at least 20 minutes in this one. So half an hour homework for you guys. It's not the most amount now, really, is it? So you should be doing these tasks pretty straightforward. I'm guessing, yes, it will take a bit longer for you guys, about an hour altogether, maybe an hour and a half, but at AS level, that's what we're expecting in terms of if you really want to progress. So remember, don't just leave this for revision at the end, do it as we go along to make sure you understand it. So, the table gives information about two beams of monochromatic light, one colour light, that's all it is. Each beam is shone in turn onto a barium plate. Beam B causes photoelectron emission, but beam A does not. A student says this because the blue beam is more energetic than the red beam. Oh, blue and red. Okay, so blue, okay, we've got over there is blue beam, okay, and red. So blue beam is beam B, and red is beam A. Okay. So, in one sense, student's answer is correct, in another sense, it is incorrect. Explain how this is. So, we've got to think about our colours and the way they're laid out. So, Richard of York gave battle in vain. Okay, we know infrared, the red end of it, sorry, is longer wavelength. So, it's going to be a longer wavelength and a shorter wavelength. So, that's a higher F, and that's a lower F. Therefore, energy increases as we go this way. So energy increases as we go that way down it. So therefore, the blue end is more energetic than the red end. Okay, so the blue beam is more energetic than red. That's currently correct. Okay, so the blue beam is more energetic than the red beam in terms of the photon. Correct. Okay. However, if you look at the intensity, that isn't the case. The red beam has a higher intensity. Okay, so that means there's going to be more photons actually coming down in the red beam. However, in the blue beam, there'll be less photons, but each of the photons has more energy. So blue, less photons, each more energy. Red, more photons, each with less energy though. Okay, so that's how it is correct and incorrect there. So correct in the sense that the red is more energetic, so blue is more energetic because it has a higher frequency, but incorrect in the sense that red actually has more photons, so it might be more energetic in that sense. Right, so explain what is meant by the term work function. Done it time and time again. Minimum amount of energy required to release an electron from the surface of metal. Calculate the threshold frequency of the barium plate. Nice, straightforward. We've got the work function. We've done this a few times before. So you've got work function is equal to h times f naught. You rearrange for f naught. So it's going to be h. So work function over h. You can tell it's a Sunday afternoon. Alright, so 3.98 times 10 to the minus 19 divided by 6.63 times 10 to the minus 34. Let's quickly work that through. 3.98 times 10 to the minus 19 divided by 6.63 minus 34. Okay, so it's about 6 times 10 to the 14. Okay, that's good. It's high frequency. It should be a high frequency. Let's check these out. Okay, so let's go backwards. So 6 times 10 to the 14. Beautiful. Energy required to move. So minimum amount of energy required to move substance, to move an electron from the surface. Okay, so maybe you've got to say from surface. Y statement is correct. We said that blue has more energy. Blue photon has more energy than red photon. Brilliant. What's incorrect? Blue beam carries less energy per unit area. Or the idea of blue per less precise. So each of the photons has less energy. We've got the idea of the fact that the intensity of blue is less than that of red. We've got that. Brilliant. Excellent. So that's the end of ISP task 1. Make sure you do work through it and use this video to check again if you need to, and ask me for any help in class if you need it. Thank you very much.